All right, our last question for the chapter. This one is definitely by far very cumbersome, but there's something magical about how these things continue to work their way in and validate the concept of magnetic charge, which is odd considering experimentally we haven't found it, but these things work so well with them. This is a cumbersome question simply because we have to check all of Maxwell's equations, so let's go ahead and dive in. The statement is, show that Maxwell's equations with the magnetic charge are invariant under the duality transform, where E prime is equal to E cosine alpha plus CB sine alpha, CB prime is equal to CB cosine minus E sine alpha, and then the charges move as such. These transforms are definitely something to note and will come up again in the relativity section. So good to get this good to get this practice in now. Clearly see here is 1 over epsilon naught mu naught, and alpha is some arbitrary rotation angle in the quote E and B space, the space of the fields. The charge and current densities of the transform in the same way as QE and QM do. And what this means is that, in particular, if you know the fields produced by a configuration of electric charge, you can immediately, using alpha equal 90, write down the fields produced by the corresponding arrangements of the magnetic charge. Okay, so a nice little hint to use. Show that the force law, F equal QE times E plus V cross B plus QM for the magnetic charge of B minus 1 over C squared V cross C is also invariant under this. All right, so the Maxwell's equations that account for the magnetic charge are given as such. The only things that really change here are the divergence of B goes to mu naught rho m, and the curl of E goes to adds on a Jm term. Okay, so now these are quote symmetric, which honestly they do look pretty, and theoretically it makes so much sense why some magnetic charge might exist, but we just have not found it. All right, so what we need to do for invariance is show that the divergence of E prime is equal to the divergence of the charge, or rho E prime, so it looks just like the equation before and after. So let's go ahead and plug it in. E cosine alpha plus CB sine alpha. Okay, clearly the divergence is only affecting the vectors here, so del dot E and del dot B. Okay, here we can plug in that we have rho E for 1 over epsilon naught, rho E for the divergence of E, and we can plug in mu naught rho m for the divergence of B, factor out a epsilon, 1 over epsilon naught, so we have to put an epsilon naught on the sine alpha term. And then what we see here is that when we do that, we're left with rho cosine alpha plus, well, now that we know that we have a mu naught epsilon naught, we can plug in a 1 over C squared factor, and the C's cancel, so we're left with a 1 over C term. So if we factor out a 1 over C term from the sine alpha term, we get 1 over C epsilon naught, C rho E cosine alpha plus rho m sine alpha. And what we see here is that that's equal to the C rho prime E transformation. And then the C's cancel, so we're left with 1 over epsilon naught rho E prime. Therefore, the divergence of this transformed field is equal to 1 over the transformed charge distribution. That's pretty darn cool. All right, so if we do a similar method and we just kind of expedite the process, we take the divergence of both, plug in accordingly from the equations, and then simplify down, and we see that divergence of B prime is equal to mu naught rho prime. Now here the curls, you got to be careful. You got to plug in the proper equations for the curl of E and the curl of B. It takes a little more work. Then we factor the current density terms to the left and the field terms to the right with their derivatives, and we see that this Jm cosine alpha minus Je sine alpha, all that is Jm prime. Again, since we were told that the densities transform like the charges, that's pretty neat. And then we see that the derivative is acting on the transformation of B prime, so the curl of E holds. Similarly, we're going to have a little bit more of a mess here with the curl of B, as always. So we have the curl of B, plug that in, the curl of E, plug that in, simplify it as much as you can. Now we get the current densities to one side and the fields to the other. We see that the current, or the curl of B, is equal to mu naught JE plus mu naught epsilon naught curl, or derivative of E prime dt, so that holds as well. Pretty sweet to say. Now for this, what we got to do is be very careful with the force law, hence the color coding. So the electric part of this, for the prime coordinates, the QE is plugged in and E is plugged in, but now we need to find V cross the B prime. And then on the next page, we have the purple part corresponding to the magnetic charge. All right, so now what we want to do is, for the electric charge, we want to factor out everything as far as what the charge and the fields can do. And similarly, we want to do that for the V cross B part. So you see how we have this charge that needs to go on to the E field and the charge that needs to go on to the B prime field. Let's go ahead and factor all those out before we try to take some cross products. What we see here is that we have E cosine squared alpha, and then a plus CB sine alpha, cosine alpha minus CB. And you see that we get a bunch of cancellations this way. Similarly, for the QE prime distributed to the B field term, we get more cancellations that way too. And then you see, similarly for the magnetic sequence here, when we do that, what we're able to do is show that after distributing yet again, V cross is the same for QE and QM. Again, a lot. All we're doing is factoring out the QE and the QM and the V cross parts for both of these independently. But this is a gigantic mess of simplifying. So pause the video if you need to see this. But it all cancels out quite nicely, and then we're left with here we're left with after that we can simplify this down to E to the QE, since that's what we're trying to show is invariant. And if we do that, we factor the E's out, we see that we get a cosine squared plus sine squared. On the V cross B parts, we see that we get a cosine squared and a sine squared. Once again, they cancel one. And similarly on the magnetic charge, once we expanded and then factored for QM and QE, we see that again we have sine squared plus cosine squared, sine squared plus cosine squared with the appropriate factors. And we see that we're left with QE is equal to E plus V cross B plus QM B minus 1 over C squared, V cross C, and that's equal to F. So F prime equals F. That's awesome. Messy, but awesome.